All right, physics nerds, it's time to learn how to linearize data. We're going to do it in 4 steps. The first one is to derive or locate an equation that links the values collected and your target value. This is going to be really easy if you're doing a experimental design question for the AP exam because they're going to give you an equation and they're also going to give you a data set that might look something kind of like this. It's going to have 2 columns worth of some data. So, um, the second thing you're going to do is take that equation and rearrange it to match a y equals mx plus b format. And the goal that we want to have here is we want to have the the uh, the slope position be matched up to our target variable. So then we also want to make sure we have one variable on the left for the y-axis and one on the other side on the right, and that'll be for our x-axis. And then we're going to calculate any new columns that are needed based on what we want to put on the x or y axis. And if needed, we're going to, and then we're going to plot and find the slope of that. Make sure that when we're done, we cite and solve. So let me go through 2 examples with you. First one is, what if you have something and you don't even know what it's about? Okay, this is an angular momentum equation, and you're not supposed to know it yet, probably in this point in the year. But you know that L is equal to RMV. Boom, we just did the first thing because we linked R, one of our variables, is boom here, and V, the other variable, is right there. And M is a constant, and that's okay because we know it. And our target is to find L in this right here. So what we're going to need to do now is step 2, rearrange that equation to match a y equals mx plus b format. Remember, we want to get our target in the slope position. So that's going to take L, and we're going to take, let's see, I guess I got it right here. Y equals mx plus b. So right now, L is on the wrong side of the equation because that's over there by where the L's go, or by the Y's go. So I'm just going to reverse my equation. RMV is equal to L. And now I have my slope comes right after the equal sign, and so does my L. And that feels kind of good. But I have a problem in that I have 2 variables on the left-hand side. I need one on the right, one on the left. So why don't we keep the R right here, and we'll leave that where the y-axis goes, and then we're going to take MV. They don't belong over there. So I'm going to divide them onto both sides. Now, when I do, I could stick them underneath the L, but instead I'm going to put 1 over MV. I'm going to divide both sides by MV. And dividing is the same as multiplying by a fraction with that quantity in the denominator. And why would that be helpful? Because now I've just decided what can go on the x-axis. This is not the only way I could do this. I could for sure show you some other ways, but this way is going to work really well. I noticed that there's no addition or subtraction, so that means there's going to be no intercept. I expect this to go through 0 and be a directly proportional equation. So what we need to do now is we need to calculate and cite and solve. So what I'm going to do is I'm going to kind of keep this up over here, and I'm going to bring up Desmos. Now I took the liberty already to type in these values into Desmos. You can see that they match the values right there. And the X column is actually the radius, and I think it's really helpful to make sure that you type in symbols here. Now I didn't just type R and V, I left it as R1, V1. That tells me that that tells Desmos that it's a series of things. And what we're going to do is make a new table because you can see that the data right here is actually curved, and that's an inverse relationship. So what I'm going to do is going to put in a new table, and this table I'm going to use to find out what the slope of my line is. I'm going to turn off my old data points like that. And what I'm supposed to put is R on the y-axis. So I'm going to take my y-axis here and put R. Now that's a little awkward because I don't want to have to retype all these. You could retype them if you want. But what I'm going to do is I'm going to tell it to calculate a value for the y-axis, and I'm going to say that should be 1 times R1. And so that just copied everything down. You could have just done it by hand, but this will be faster. Now the second column, which is going to be column X, should be 1 over mv. So I'm going to do 1 divided by the mass, which is 200,000, and then V1 right there. Okay, and that will work. Another way you could do this if you wanted to is you could define M equals 200,000. And then if you did that, then because you've told Desmos what M is, then you can stick an M right there and it doesn't change it. See, if I didn't have this here, it would be like, I don't know what to do with that. But if you define your constants, then you can write your expressions there and it'll feel a little bit more like you're doing physics. So let's take a look here, and I can see by zooming that this is linear. That's a good thing. And I can click the button to add a regression, and this linear regression has a value of y equals 1.4 x minus 136. So when I go to cite, what I'm going to do over here, we calculated a new column, by the way, and maybe I should talk to you about what that's going to look like on paper. On paper, I would put 1 divided by mv. That's my that's my header, and then I'm supposed to put units too. Well, that's a problem. I guess I could put 1 over kilograms times meters per second, and that for sure would make sense. And so what would the units of my slope be? Well, I know that really my slope is going to be equal to y over x. So in this case, my slope is L. It's going to be equal to r divided by 1 over mv, or in other words, r times mv. Hey, that's where we started, isn't it? If we look at what the units are going to be, the units for the distance is measured in r and meters, and the units for mass is measured in kilograms, and the units for velocity is measured in meters per second. And so this is going to become kilograms times meters squared per second. So what I'm going to do here is I'm going to cite. Cite meaning I'm going to tell my reader where I got this. I got from a Desmos linear regression. I got y is equal to 14 times 10, well 1.4 times 10 to the 14th times x minus, I forget the other number, 3s and 6s, 1.36. No, that was 136, my bad. So what does this mean? This means that the slope is equal to 1.4 times 10 to the 14th. What were those units we came up with before? Kilograms, meters squared per second. Okay, that's what my slope is. And I had said that L is equal to the slope earlier. And so that means L is equal to 1.4 times 10 to the 14th kilogram meters squared per second. Okay, circle this to let them know that that's our answer. And boom, we got it. That's how we linearize. I am prepped to do one more with you, so let's do one more. This one has an equation that we should be more familiar with. Distance is equal to 1/2 of at squared, but when you're slowing down due to friction, that might be equal to mu g. Whether or not this is right, we can still deal with it because our goal is to find the coefficient of friction. That's going to be mu. And we have a distance on the y-axis. I don't know. It said it's on the y-axis yet. I'm already thinking ahead. The time here is going to be another variable that's kind of near the x-axis position, and you could do it like that, but then what are you going to do with your g and your 1/2? You can't just drop them. So we're going to follow the steps. First step is identify an equation, has all the stuff we need in it, and other things are constants. G is a constant, 1/2 is a constant. Second step, get it formatted in a y equals x plus b format. It's already got distance on the y. I'm gonna prioritize putting mu in front. We can rearrange multiplication, so I'm gonna put the mu, the coefficient of friction, in where the where the slope goes, and I'm just gonna put everything that's left over on the x-axis. That's gonna be half of g times t squared cut in half. That I think is the way I'm gonna choose to format it today. And that's going to go right here for our x-axis. I see no addition or subtraction, so therefore there's no intercept. So what I'm going to do is I'm going to make a column here that's going to be made for gt squared over 2, and it should have units of g's units of meters per second squared times a time unit squared. And so that actually should just be meters. And then I'm going to take half of 10 is 5 times 0.4 squared. Figure out what that is. Is that 0.9? I don't know. So I'm going to come up with and do all that. Now I'm going to use Desmos, and I recommend you do too. Okay, we're going to get rid of this one. And don't worry, I've got it already pre-built over here. Oh, actually I did too much there. I've got it all pre-built right here. I've already coded it as D1 and T1. That way I don't forget which one's which. I can see that this is not a linear function. It's curved. And so I'm going to turn it off, and then I'm going to do what I said I would do is put my y-axis, put a new table. Y I'm going to change to be equal to the distance, right? The distance goes on the y-axis. So I'm going to put 1 times D1. Okay, on the x-axis, I'm supposed to put gt squared over 2. So I can go here and I can define my g value. And then that's going to let me to do gt1. You do have to put the 1 there. Squared divided by 2. And that, oh, I did bad math earlier. I said it was 0.9. But that would have been 0.18 times. Yeah, okay, so this is 0.8. Cool. All right, so this is why we don't do mental math. It's because we make mistakes. So I'm going to zoom to fit. Oh, it's so linear. Looks great. I'm going to hit my button to linear regress this here. And now I'm going to go and cite my equation. My equation here, it's this guy. And I come back over here, paste that in. Okay, you guys don't get to do that. You're going to have to type it out. That's okay. I'm just going to say this is my linear regression from Desmos. Why am I saying from Desmos? It's because different tools use different regression techniques. And so that right there tells me that. I'm going to grab this right here and say this is the slope. And that's equal to the coefficient. And so, therefore, that coefficient is equal to 0.734. And I don't need any more than 3 sig figs. This is AP Physics, people. And so there we go. We got ourselves a linearized graph and an answer from what the slope is. This is also really helpful for helping us to figure out what we should do when we're planning a lab. When we're planning a lab, we can go find equations that have the variables we're investigating and make sure that we're collecting all of the constants that are needed, because you could see that we needed the mass in this previous activity here, in this previous data set, we needed that. And so it can help you know what you need to collect as well. If you would like to practice some more with this, I will be putting in the description to this video, I'll put a link to this set here that's got 5 different, well, it's really got 6 different sets here. And if you want to know if your answer is right, you can just hit equals. Well, yeah, I'm probably going to make it non-editable. But if you just hit equals and then click on E5 here, it'll tell you the answer to the first one is 20. But you can always make a copy of this data, of this sheet for your own purposes, and then play with it. Best of luck. Let me know what more you need help doing so that I can prep you some videos for those things too.